Welcome to Coffee Break. I'm your host, Dana Curtis, and this is episode 4 of season 15. Here at Coffee Break, we invite you to join us as we dive into the fascinating world of all things microchip technology and about the time it takes to enjoy a fresh cup of coffee. For those of you joining us for the first time, Coffee Break is a live broadcast, so let's take it over to Aliyah Fahout for some housekeeping items. Aliyah, what do you got for us?
Thanks, Dana. And hello, everybody. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn. And we invite you to participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after this episode. If you're watching us on YouTube today, make sure to subscribe to our channel and click the bell so you know when we're live and when our next episode is. If you're watching us on LinkedIn, make sure to subscribe to the event so you can get all the information related to this episode. Back to you, Dana.
Thanks, Aliyah. Today we have a very special guest joining us. Doug Anderson is the Senior Business Development Manager here at Microchip Technology, joining us on Coffee Break to talk about how you can pick your power here at Microchip. Welcome, Doug.
Yeah, thank you, Dana.
Let's start with the obvious question. Why do we need power?
Well, power is what brings technology to life. Without power, we can't really do anything. We can't have a sensor, we don't have control, we don't have communication. But for me, when it gets interesting is when we're talking about high power. You know, the power to charge your electric vehicle, to run your industrial factories, to keep the data centers going. That's when it starts to get interesting to me. That's the space that I live in. And Microchip, we have a very broad portfolio of power products, making it easy for our customers to pick their power and design things in.
Right, because we're going to need more power as we evolve with our electronics. Right?
Absolutely, yeah. Everything is asking for more power every day. Yeah.
So when we talk about the concept of electrification of everything, there's a couple of trends that we see out in the marketplace, right? Industrial, data centers, as you mentioned, e-mobility, sustainability, and then of course, aerospace and defense. But it goes deeper than that, right?
Quite a bit deeper than that. And you know, let's talk about a couple of examples.
Okay.
Aviation, the electrification of aviation is really taking off,
right,
quite literally. For example, you know, here in Phoenix, we have companies that are using drones to actually make deliveries. eVTOL, which is electric vertical takeoff and landing vehicles, which you know, kind of the taxi of the future.
Yeah, you see we got it down there in the lower right.
And then even passenger planes are starting to move towards electrification. Now, of course, that requires very high power, robustness, lightweight, and so we have solutions for all of that. Another example is in maritime. There's a lot of movement towards electrifying ships, ferries, a lot of different things, even ships that are at dock. They're wanting to get them off of running their diesel generators and getting them plugged in. A unique example that we heard of recently is the electrification of tugboats. And you know, electric motors, one of the nice things about them is they have pretty much instantaneous high torque.
Right.
And if you're a tugboat needing to push around a big ship,
Precisely what you need.
That's exactly what you need. And not only that, it lowers emissions, it makes it quieter, it really fills that niche. And as you can see from this slide, it's all over the place. I mean, it's literally everywhere.
Yeah, so it's easy to think about small things like key fobs or even drones are kind of small format, but now we're getting into really big things. You're talking about mass human transport, you're talking about boats, I see heavy duty vehicles there with the tractor. We're really talking about big power now.
Big things, yeah. And not just tractors, but you know, mining vehicles and things that are just gigantic.
Earth movers.
Earth movers,
okay.
all kinds
All right,
of
so when we
things.
say pick your power, what are we talking about there?
What we're really talking about is choice. You know, how do you match the technology to your specific application needs? And you know, what we're showing here across this, it's showing the switching frequency, but it's also showing a variety of technologies. And if we start at the right with silicon, standard silicon, that has a role. And as you move over, you get hybrid between silicon and silicon carbide, and then you move into RF and microwave. And it really just kind of depends on what your application needs. And you know, what we try to do is work with our clients to approach each design objectively and recommend the right technology for their application.
We have a very large range of options.
Very large range of options, that's right.
And that leads us to implementation now.
That's right. And you know, this center, if you look at it, it's how are we delivering that to you? Is it in a die? Is it in a discrete part? Is it in a module? And really what we have is a variety of different options here so we can meet our customers where they are.
Right.
So for example, if you're designing a pacemaker, volume, how much space the circuitry takes up, plays a big role. And we're working with several clients, and they're using silicon carbide because it takes up a smaller volume, which means they can have a bigger battery,
right.
which then means that they don't have to go in and replace that pacemaker for an additional 3 or 4 years. And as you can imagine, that's quite an invasive surgery, and so they would like to extend that out as much as possible. So that's one option. Now at the other end of that spectrum, where we're showing the hybrid power drives, this is a complete solution. This is extremely high power. We're building everything into one thing to make it much easier for our clients to take that and drop it into their system. So they can focus on what's important to them, and we can kind of take off some of the power burden.
Yeah, and I see their ultra-low inductance, which we'll talk about later.
Yeah, absolutely.
And then we get into performance factors.
That's right, and you know, if we look, starting at the origin there, you know, I show standard, there's industrial, automotive, aviation, defense, space. These are the grades. These are the different types of grades. Each one of those grades has a different requirement for robustness, a different requirement for qualifications.
ISO standards and such?
ISO standards, ruggedness, reliability, each one of those. As you can imagine, if you've got something in space, it's not that easy to send somebody out to fix it.
You can't send a mechanic up.
That's right.
Yeah,
That's
we
right.
talk about that a lot.
So we're really uniquely positioned to go from standard consumer grade all the way to space grade, and that's a really unique position in the market. Now going down that blue line, you know, moving from a standard part, you then can go into a derivative. And mostly this is where we're talking about modules, where we'll take a standard module and we can tweak it for what you need. And
based on customer specific
Based on
requests,
customer
right?
specs, exactly. And then we can also do full custom. You know, if what we have in our portfolio doesn't meet your needs, we can do full custom. And again, we're really uniquely positioned in the market that we can move through that very quickly. So, and you know, all of this, the one nice thing is all of this comes from one supplier, and it gives our customers the flexibility that they need to pick their power.
Right. Okay, so this is from the component side, but what if we have a need-based, where they don't
Sure.
necessarily know what they want?
Yeah, that's a great question, and this is a different way of looking at the pick your power. And what we're showing here is we've got 3 axes here. We've got frequency, which we had on the last one. We also have device operating current and power output. And so if you have a good idea of what your overall design requires with regards to those three, then you can kind of see where, from a technology side of things, it fits. And again, you know, one of the things that we want to make sure is that as our customers are doing their designs, that they don't either over-design or under-design their product. You know, over-designing leads to higher costs, under-designing leads to failures. And so we want to make sure that that they understand where they fit on this, and we're more than happy to help folks make
Nice
those
to see we have a
selections.
range there between kilohertz, kilowatts, and
Yeah,
so
absolutely.
why don't we talk about one of the things that really matters in power management, which is thermal management. Power generates a lot of heat, right?
It does. You know, and that's one of the most important aspects of power system design is what are you doing with thermals? And really what it is as you're generating power, because it's not 100% efficient, as you said, it generates heat. And heat can impact performance and reliability over time. And so one of the things we're always looking at is how do we get that heat out of the system? Right. And when you're talking about systems that are generating kilowatts or even up to megawatts, then the heat that you're generating, it gets fairly significant. And so you have to understand and manage the thermal pathways. You have to understand how to choose the right packaging and mounting, the right heat sinks. All of this becomes very critical. And you know what we're showing here on this slide is our power surface mount topside cooled package, and PSMT for short.
It's quite a heat sink on
It's
there.
quite a heat sink on there. And what you'll notice is most surface mount packages have the heat sink on the bottom. And so when you mount it onto a PCB, most of them are going through a reflow process, and so it's just soldered to the board.
Right.
The PCB is not the greatest thermal conductor out
Right,
there.
yeah.
And so one of the ways that we can help to get that heat out is by having the heatsink move, or the thermal pad move to the top, then you can mount a heatsink directly to it. Now the board that we're showing on the left actually shows a couple of those parts mounted. In the middle of that board, it shows those same parts with a thermal sheet installed, and then the last one shows it with the heatsink installed. Now, interestingly, sometimes, I mean, that's a really big heatsink. And some of the designs, the parts will actually be mounted right up against the housing, the housing of the component that's being designed. Sometimes it's air cooling, sometimes it's liquid cooling. And so we work with clients to figure out what is the best for them.
Flexibility is a big part of that.
Flexibility is a big part of it.
Okay, so now we get back to that low inductance we were talking about.
Yeah, so when we're talking about, what we just showed in the PSMT, that's a discrete part. Power density is a big topic, and one of the best ways to increase your power density, or watts per cubic inch or cubic centimeter, is to move to a module. We take care of a lot of the heavy lifting when it comes to the design, and this is our SP6LI, which is an ultra low inductance design. And as we're designing these, we're also keeping in mind just what it means, thermal management. And when we're doing the design, we start with the substrate, and we look at what is it that we need to do to effectively transfer heat from the die through the substrate into the base plate. And we have a variety of different options that we use, again, depending on needs. And the substrate, in addition to thermal conductivity, it also provides electrical isolation, which is another very important part of that. And then after you've picked your substrate, then you go on and you pick your base plate. Now our standard base plate material is copper, and this is really good for transferring thermal out. Where it can, slow down a little bit is the coefficient of thermal expansion is actually pretty high on copper. And what that means is when it heats up, it expands, and so it moves. Yeah. And so if you have an application where you're going to be going through a lot of different temperature cycles, hot, cold, then that could lead to some reliability issues.
Expansion and contraction.
And so in applications that require that type of thermal cycling, then we would opt for the ALSIC. Yeah, because it doesn't deal with heat quite as well, but it does really well with thermal expansion. And so, see, these are just some of the examples of the design choices that we have to go through.
We're getting back to choice.
That's exactly right. And by making those choices, it allows the power modules to operate at higher levels, at greater reliability, and be far more robust. And so it really gives the customers a shorter path to a full design while avoiding some of the common thermal bottlenecks in a design.
Yeah, now I see here we got something about parasitic resistance. Can you touch on that?
Yeah, so parasitic resistance and parasitics in general in modules are something that we have to deal with. Now, in this particular one, we focused more on actually the induction than the resistance. Okay. And the reason for that is as you're talking about really high power and fast switching frequencies, even nanohenries of inductance can have an impact. An impact on the efficiency, on EMI, on a lot of different things. And so that's where we focused on this, but we are always looking at all of the different stray inductances and different things like that.
Okay. With that, let's get over to Aaliyah for some questions from the interwebs. Aaliyah, what do we got?
Awesome. Let's start with the first question. How does the top side cooled package compare to the bottom side cooled D2 pack from a thermal performance perspective?
Okay. Well, both of those packages are surface mount packages, which means that they're suitable for high volume manufacturing. The PSMT has the heat sink on the top. The D2 pack has it on the bottom. And as we talked about earlier, PCB material is just not the best material that there is for heat transfer. Right. So by having that, the PSMT, because it performs better, it improves both our continuous and pulse power capacity. We did some experiments where using a program called Inisys Ice Pack, we did some simulations between the two. And at the same power level, at 20 watts of power dissipation, the PSMT runs about 35 degrees centigrade cooler than the D2 pack.
That's significant.
Yeah, so it's a pretty significant change there.
Okay.
Awesome. Your next question is, the base plate options listed are copper and AlSiC. How do they compare?
Ooh, good question.
Yeah, that is a good question. So, and again, when we're looking at base plates, we're looking, the two main things that we look at, we kind of spoke about a little bit already, are thermal conductivity and thermal expansion. And because with silicon carbide in particular, and some of the higher frequency devices, because they're switching so fast, the better that we can control that, the switching losses, then the better, the cheaper that you can design your system.
So cost is a factor.
Cost is a big factor. And one of the big factors is, because you're able to switch faster, you can use smaller magnetics. And magnetics can be quite expensive. Of course, they take up more room. And so again, that higher switching frequency allows you to get to higher power densities. A rule of thumb that we use is below 20 kilohertz, IGBTs is probably the right way to go.
Right.
It's still very cost effective. And IGBTs are very well suited for high current and mid to low frequency applications. Now, when we talk about conduction losses, IGBTs work the best when they're working at their full power rating. As you start to back off, you end up with a voltage drop, a VCE voltage drop that's always there regardless of the load. So, you're losing things, you're getting less efficiency at lighter loads. And that's for the conduction losses, where MOSFETs are efficient across the entire operating range. And so if you have a load, an application where the load is going to vary, and if it's going to be running at a low load for a lot of the time, MOSFETs, silicon carbide MOSFETs, may be where you want to go. But again, it's really about picking the right device for the job.
Based on intended use, right?
Based on intended use. And again, what our goal is to help guide our customers to the ideal part for their application. So.
Perfect, thank you.
Yeah.
Here is a LinkedIn question for you. What are key considerations when deciding between SiC MOSFETs and IGBTs?
So that was kind of what we talked about in the last one. It really depends on the frequency, the loads,
You talked about
characteristics.
variability in SiC, but
Yeah.
IGBTs are more, they kind of have more of a specific use, right? Like running them at a really, really hard rate.
Really, really hard rate. Silicon IGBTs can actually go up to a much higher voltage as well. We're talking tens of kilovolts, where silicon carbide right now will get to those voltages eventually, but commercially, about 3.3 kilovolts is where it's at. But yeah, it really kind of goes back to what is the application signature and what does it fit in? And are you switching really high frequency? Because if you are, then you're going to want to lean towards silicon carbide. If you're switching below 20 kilohertz, you're going to lean more to IGBTs. If you're doing hard switching, you're going to probably want to lean towards silicon carbide.
Yeah.
If you're doing 0-volt switching, then IGBTs are a little better suited. So again, really, we kind of have to look at the mission profile.
Yeah, there is crossover, but
Yeah.
there are specific areas where one is better than the other. Okay.
Absolutely.
Awesome, thank you. Here's another question for you from LinkedIn. What is hybrid IGBT and how does it differ from a regular IGBT?
Hybrid.
Yeah, that's a really good question. And so a regular, in quotes, IGBT is a silicon IGBT paired with a silicon freewheeling diode. So in this traditional setup, it trades off, there are trades-offs in terms of speed and losses. And so a hybrid IGBT keeps the silicon IGBT, but then changes it out to a silicon carbide diode, and they put it into the same package. And so by doing that, you reduce your reverse recovery loss, you increase efficiency, and this is a big deal during switching, especially if you're in a hard switching application. So again, it really all comes back to being able to pick the right thing for the right
But we have a solution.
We have both, yeah. We have a solution for both.
Great, thank you. I can do one more question. Why would I choose an ultra-low inductance module?
Okay, like the SP6Li. So when you're working with fast switching devices, especially silicon carbide MOSFETs, the parasitic inductance becomes a major performance limiter. And so our goal when we designed this was to get the inductance as low as possible. So, with as few as, as little as a few nanohenries of stray inductance, it can have an impact on it. And so when we do the layout of the modules, we look at everything to make sure that we can minimize that. Because by minimizing that, we minimize switching losses, EMI issues, we increased robustness. It makes it, eliminates failures over time. And so you're minimizing the loop inductance within the module. Outside of the module, you still have to be concerned about how you're designing your board and everything else, but this allows the customers to really take full advantage of what silicon carbide has to offer.
When reliability is key, right?
When reliability, again, it's higher efficiency, higher switching frequencies, and better thermal performance by having that low inductance. Good questions.
Awesome. Thank you, Doug. Those are all the questions I have for you today. And for the audience out there, if you have additional questions or comments, please email us at livestream@microchip.com. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Dana.
Thanks, Aaliyah. That's all the time we have for today. Special thanks to Doug for sharing his knowledge and passion with us today. If you'd like more Coffee Break, head over to microchip.com/coffee break and click on the subscribe button to get updates for all things Coffee Break. You can also see upcoming episodes for Season 15. And of course, be sure to join us next time on Coffee Break as we explore unique QPL 25 amp power relays for harsh environments. That's going to be a good one. Until then, stay curious, stay creative, stay caffeinated.
You guys are good, clear.